In the movies, when a bomb hits a target, it explodes immediately. There is a flash, a boom, and a fireball. But in the real world of high-stakes warfare, an instant explosion is actually a failure. If you are trying to destroy a command center buried 5 stories underground, or a nuclear centrifuge hidden inside a granite mountain, a surface explosion is useless. The blast wave follows the path of least resistance. It bounces off the roof and dissipates into the air. The general sitting in the bunker below won't even spill his coffee. To kill a bunker, you don't need fire. You need a drill. You need a weapon that can travel at supersonic speeds, slam into solid reinforced concrete, and survive the impact without detonating. And then, and this is the engineering miracle, it needs to think. It needs to count the floor as it passes through them. Roof, floor 1, floor 2, floor 3, now. In today's video, we are analyzing the physics of this weapon, the Bunker Buster. We will explain how the US Air Force built the first one in just 3 weeks using old artillery cannons, how they engineered a fuse that can survive 10,000 Gs, and how these weapons use accelerometers to feel their way into the basement. So the story begins in January 1991, during the Gulf War. The US Air Force had a major problem. Saddam Hussein knew the air war was coming, so he buried his vital command centers deep underground, protected by feet of steel, reinforced concrete, and the earth itself. The standard penetrating bomb of the time, the BLU-109, was failing. Pilots reported that their bombs were literally bouncing off the roofs of the bunkers. The casings were too thin and the warheads were too light. The Air Force needed something heavier, harder, and narrower. And they needed it now. And so they initiated a crash program codenamed Deep Throat. Engineers at Eglin Air Force Base did not have time to cast a new bomb body from scratch. That takes months, so they improvised. They went to an army surplus yard and found old rusted gun barrels from M110 howitzers. These barrels were made of incredibly dense hardened steel, designed to withstand the massive pressure of firing artillery shells. They were perfect. In a feat of MacGyver engineering, they cut the barrels to length. They machined a heavy pointed nose cone and wheeled it to the front. They hand-filled the tubes with molten tritonol explosives because the standard filling machines could not handle the size. And so, in less than 3 weeks, they invented the GBU-28. It was a 5,000-pound monster. You see, the timeline was so tight that when the first 2 operational bombs were loaded onto the transport plane to fly to Saudi Arabia, the green paint on the casing was literally still wet. They dried in the air during the flight. Hours after landing, they were bolted onto F-111 advarks and dropped on a bunker complex north of Baghdad. And the result? Well, the weapon punched through the concrete roof, penetrated 3 floors, and destroyed the target. That's when the era of the Deep Penetrator had begun. But making a heavy bomb is only half the battle. The real physics challenge is survival. When a bunker buster hits concrete at Mach 1, the deceleration forces are astronomical. The impact force can hit 10,000 Gs. For context, the human dies at roughly 100 Gs. A normal car crash is maybe 50 Gs. At 10,000 Gs, steel wants to bend and electronics want to shatter. If the bomb has a blunt nose, it will smash itself to pieces on the surface. If the nose is a simple cone, it might stick. This is why the bunker buster uses a specific mathematical shape called the ogive. It is a curved, tapered point similar to a Gothic arc. This shape doesn't just cut the concrete. It pushes the material outward radially. Under the immense pressure of the impact, the solid concrete temporarily behaves like a fluid, flowing around the bomb body. This reduces friction and prevents the bomb from shattering. But the bomb body is just steel. The fuse, the electronic brain, is delicate. To ensure the fuse survives the crash, engineers encase the entire electronic assembly in a special epoxy resin potting. This turns the circuit board into a solid brick. It absorbs the high-frequency shockwaves that travel through the metal, ensuring that the microchips stay attached to the board even as the bomb is smashing through 10 feet of granite. So, the bomb survives the impact. It is now traveling through the roof, but the target is in the sub-basement, 4 floors down. In the old days, fuses used a simple time delay. You would set the fuse to explode 0.5 seconds after impact. But what if the roof is thicker than you thought? The bomb might explode halfway through the concrete. What if the roof is thinner? It might bury itself in the dirt below the floor. In any case, time is unreliable. You need to count space. Modern bunker busters use a piece of technology called the Hard Target Void Sensing Fuse. It uses a highly sensitive accelerometer to measure G-force in real time. Here is the algorithm. It runs in milliseconds. 1. Massive deceleration. I am hitting the roof. Concrete. 2. 0 Gs. I am falling through air. Room 1. 3. Massive deceleration. I am hitting the second floor. Concrete. And 4. 0 Gs. I am falling through air. Room 2. The weapons officer programs the fuse before the flight. Detonate after the 4th void. The bomb literally counts the floors. Crunch 1. Fall. Crunch 2. Fall. Crunch 3. Fall. Crunch 4. Boom. This ensures the explosion happens exactly where the enemy is hiding, turning their own protection into a containment chamber. Now, you might be wondering, why is this deep detonation so deadly? Well, it comes down to the physics of confinement. If 500 pounds of explosives detonate in an open field, the pressure waves dissipates rapidly in all directions. The kill radius might be 50 meters. But inside a bunker, the laws of physics change. The shock wave hits the wall, bounces back, hits the other wall, and bounces back again. This is called reverberation. The waves stack on top of each other, creating a complex web of pressure that lasts milliseconds longer than a standard blast. The amplified overpressure doesn't just knock you down. It liquefies internal organs. The pressure difference ruptures lungs and causes massive internal hemorrhage. The structure itself, pressurized from the inside like a balloon, often lifts off its foundation and collapses. Now, as bunkers got deeper and concrete got harder, the GBU-28 wasn't enough. Enter the GBU-57 MOP. MOP standing for Massive Ordnance Penetrator. This is the modern heavyweight champion. It weighs 30,000 pounds. It is so heavy that only the B-2 stealth bomber can carry it. Literally, there is only one plane on this earth that can carry this weapon. It is designed to kill targets that are legally untouchable by nuclear weapons. It can dig through 200 feet of earth and 60 feet of reinforced concrete before detonating. It is a weapon designed to reach the deepest, darkest places on Earth, like nuclear facilities hidden inside mountains in Iran or command centers deep under Pyongyang. It is the ultimate triumph of material science over architecture. The bunker buster proves a grim rule of modern warfare. You can hide from a camera. You can hide from a satellite. You can hide from radiation, but you cannot hide from physics. As long as nations build deeper holes, engineers will build smarter, heavier drills to find them. The days of being safe underground ended the moment the Air Force decided to turn a cannon barrel into a bomb. If you enjoyed this look at the smart fuse, make sure to subscribe, hit that notification bell, and watch our next video. Thanks for watching.